Hello, everyone. My name is Jonathan Schaeffer, and it's my pleasure to be part of this year's Advances in Computer Games Conference. It's an absolute delight for me to be able to introduce today's keynote speaker, Professor Yngvi Björnsson from the Department of Computer Science at Reykjavik University. Yngvi worked for several years in industry before he came to the University of Alberta in Canada in the mid-1990s. He was part of this trio of outstanding PhD students that was privileged to know and work with at that time. Aska Platt, who is in the Netherlands and did a lot of work in games research. Andreas Jungens, who is in Berlin and works in the automotive industry. He also did games research and single agent search. And of course, there was Yngvi, our Icelandic Viking. While at the University of Alberta, Yngvi got heavily involved in ICGA activities. He and Andreas wrote a program, I believe it was called the Turk, that competed in the World Microcomputer Chess Championship. Probably in 1996. And he also got involved in writing programs that competed in the Computer Olympiad, most notably with Lines of Action. He graduated with his PhD in 2002. Tony Marsland, who's also at the University of Alberta, was his supervisor, and the PhD thesis was on game tree search. After graduating, I was fortunate to hire Yngvi to work as a postdoc with me. Among other things that he worked on, we had him work on some improvements to our checkers database code. And in 2007, we solved the game of 8x8 checkers or drafts, and that resulted in a paper in the journal Science. And Yngvi was deservedly a co-author on that very important paper. He left Edmonton in 2004 and joined Reykjavik University, where he has been for the past 21 years. Time flies, right? During that time, he's published many papers to do with AI and games. He also was very active in the general game playing community for around 15 years. There was an annual competition at the AAAI conference to build programs that could play any game given just the rules of the game and a short learning period. The program had to play any game that it was given. And Yngvi was part of the team that won the general game playing contest 3 times in 2007, 2008, and 2012. As I said, he's been at Reykjavik for a long time. Because he's got such seniority, he had to pay his dues, which meant that he had to serve as chair of the department for many years. He's also been very generous in his service, not just to the university, but also to the community. He organized the World Computer Chess Championship, which was held in Reykjavik in 2005. And during David Levy's tenure as ICGA president, Yngvi served as vice president from 2005 to 2011. Anybody who's worked with Yngvi knows him very well to generally always be smiling, quick to laugh, a real delight to work with. And so it is my great pleasure to introduce today's keynote speaker, Professor Yngvi Björnsson.
Thank you very much, Jonathan, for the nice introduction. Hello, everyone. I'm very happy to be here. Kind of a Jonathan's introduction brought me back down the memory lane when I was like my first ever academic talk I gave was at, I think it was at the sister conference, like not ACG, but Computer and Games. And I remember how stressed I was back then, my first talk ever. And there was the last talk of the day, and there was someone sitting in the front row who was kind of nodding or falling asleep during the talk. That made me feel even worse. And then later we went out. This was at Maastricht. We went out for dinner, and that person said that this was actually quite a good conference. I only slept during one talk. This made me feel even worse. And then I found out that this was Ken Thompson later. And then, yeah, okay. So, but I'm feeling much better now. Thank you, everyone. But nice to be here. So I want to talk about explainable AI in chess. So as we saw during the introductory talk by Jon Edwards, like these silicon monsters are now, these computer chess programs are playing superhuman chess, almost being unbeatable. And chess has always played a big role as a testbed in artificial intelligence. And now that they have reached this superhuman level of play, what does that mean for the future of chess and AI? So what's next? And again, while they do play very close to perfect play, or at least they're hard to beat, can we learn? Can they teach us anything? And that is kind of what this talk is about. I'm going to spend the first little, maybe 1/3 of the talk talking about the past, what led us to the point where we are at today. But mainly I'm going to focus on hopefully what I see, what lies ahead for chess and AI, and especially like its role in explainable AI. And as a case study, I'm going to talk about somewhat recent work with a PhD student of mine, just as one example of how chess can serve as a good domain for explainable AI. So board games have, like I said before, played an important role in AI research, and they were at the very, very beginning chosen as a good test domain because they have simple rules but complex strategies, and in a way give the AI researchers a laboratory settings. Like it's much more predictable than the real world. So that was kind of a good way to start, and you can kind of control the complexity of things. So it made kind of ideal test bed for studying research, doing research in artificial intelligence. Especially, at least at that time, it was thought that to be able to play games at an expert level, one had to bring to the table many kind of these human-like intelligence properties, like logical thinking and intuition and even creativity. And from very, very early on, the birth of AI and kind of the term AI was kind of coined at the Dartmouth workshop in 1956. And this is often like unofficially been talked about as the start of our field. Chess was being discussed there as a nice testbed for further AI research. But even before that, chess had become caught the eye of these researchers, and they were kind of Alan Turing was doing work on his TurboJump program before that, and there's even a recorded game that the program supposedly played, and he didn't have a computer to run the program on, so it was basically hand simulated the result. Shannon's seminal paper and others' work was already being done before that. But around this time, there was we got the first running chess program playing of the full game of chess on a full 8x8 board. Previously, there had been some programs running on smaller boards. There had been programs running on a full board that could only do some mating problems, etc. But the Bernstein's is kind of attributed as the first program that played chess. It took it like many minutes to make a move. It was running on IBM mainframe, but since then there have been a continuous development and to the place where we are having these superhuman programs today. But originally, researchers thought that this was a much easier quest. So first, let's just have programs to play chess. Then we can start to deal with the real life problems. And there was even a prediction that a computer would become the world champion in chess within 10 years. And it's kind of and there was a lot of excitement about AI at this time and lot of optimism. And it kind of reminds me a little bit of today's hype about this large language model and generative AI, where you hear kind of a claim similar to those from the early days. And there was basically within 10 years we will have a computer being world champion, given there was one caveat they gave, given that they would be allowed to be world champions. This actually became contested later when Jonathan Schaeffer Chinook actually did beat Tinsley and became the first program to be a world champion in any game. And then it was actually a little bit debated at that time if a computer should be allowed to become the official world champion in a game of skill. And the quest, it took many years, and David Levy's famous bet that he repeatedly was betting even 10 years into the future, making bets that no computer would win him in a match. He made it in 68, but 10 years later he played a match that he won. Then kind of the horizon became a little bit shorter, 5 years. And eventually he lost to Deep Thought in 89. I think at that point it was not really an official bet yet, but basically it was the writing on the wall, what was to come. And then, of course, like the famous Deep Blue computer came about and did win, played 2 matches against the Kasparov, lost the first, but they won actually a game there. And then it narrowly won the second match. And kind of finally, 40 years after the original kind of a prediction, finally, the computers were playing at this level, similar level as the best humans. Of course, there was a lot of effort that went into this, both specialized hardware. There were grandmasters working on the team. There were a team of experts, computer and chess experts, working for decades to get the knowledge into the program, etc. And the research focus there was very much based on alpha beta like search algorithms and basically decoding the chess knowledge as they could be used effectively by the programs. So the evaluation functions were mostly handwritten and possibly tuned a bit automatically by a computer, but there was a lot of manual effort that went into making these programs. Then, if we talk about the modern era, there was a new search paradigm that came very popular and is still today, this Monte Carlo tree search. The evaluation function changed from being handmade to become learned and using neural networks to evaluate the merits of game states. And this kind of AlphaZero like kind of a learning where you are using this Monte Carlo tree search and to learn to play, and the neural network to evaluate the game states became kind of the standard approach. Stockfish was kind of one of the strongest chess program there, and I think one thing also I want to say was good for the computer chess community is we moved from being the strongest programs being proprietary software to becoming open source software. And Stockfish was kind of one of those programs that was one of the strongest and for the longest time the strongest publicly available program, at least. And it was still using the old alpha beta based search paradigm, but it had at some point had both hand handmade evaluation, but also neural network. And as you will see later, this allows us to actually compare what kind of the neural network learned that the hand evaluation functions didn't know. And the research focus then changed on this Monte Carlo tree-search-based algorithm, and this is still a very active research area. There's actually a talk tomorrow, invited like a keynote talk about that. And learning to play automatically. And there was a very notable milestone there when the AlphaZero kind of first AlphaGo and then later AlphaZero came. Like we said, in like 97, Deep Blue was playing against beat Kasparov. The PC programs followed like in the next decade or so, but there was a lot of manual effort that went into making those. Where at AlphaZero, just giving the rules of the game, was able to learn in time span of a few hours to play better than any entity on Earth. And so, and just playing against itself. So this was again a major milestone. And so now, where does that leave us? We have these AlphaZero-like players now that use Monte Carlo tree search, and then they automatically learn both to evaluate the state space, have so-called value function, but also to learn kind of a probability distribution over what are good moves, the policy. And we have these, and like AlphaZero from DeepMind learned not only to play chess, it was general enough to be able to learn to play several board games at a world-class level. So it was chess, shogi, and Go that it was playing basically at all three at the superhuman level. So now the question is this strong or weak AI? So you're playing stronger than any entity on Earth, not only one game, but several games, and we learn it automatically from self-play. So are we not done? Well, let's look at this a little bit more. Donald Mickey in '88 put down a criteria about what we mean by having a good machine learning system. And this was kind of I got this information from an article that Ivan Bratko reminded me up, like he wrote in 2018 as a reply to when AlphaZero came out. And we have only kind of touched the surface in what we want to get from systems like these. We want a learning system that learns and improves performance by acting, and definitely AlphaZero is doing that. But we also want systems that it can tell us what it has learned. And that is the second criteria. And the third criteria is we want to not only want it to explain it to us, but we want to explain it in a way that we can learn from it effectively. So we can become better at the task from the knowledge that the computer has gathered, and it is able to teach us that. And this is very, very, very much still lacking in the super strong game playing system that I have today. And this is where I think is the kind of a next front in AI research, and games, and especially chess, I think can play an important role, is to now we have this system that we're able to learn new knowledge that is we didn't know before. And how can we learn from these systems? And this is like where explainable AI comes in. And we want, like, given a game state, you want to basically know which side is better and why. And this has been done, like, explainable AI has now been very active research area in trying to understand, like, neural networks. But games, a decision in games is based not only on what comes from the model, we also have this think ahead part to games. We have to explore many possibilities, we have to evaluate the resulting states, and based on that, we have to make a decision. So the decision making is not only based on a model, like in many other domains where we are predicting things in finance or health, just based on a trained neural network or some other model. We are making a decision here based on both a trained model, but also on exploring, doing the think ahead part where we have to explore many possibilities. And this has sometimes been called kind of explainable search, search interpretability. And games combine these two aspects of decision making, making them quite challenging. And for example, it's not sufficient to explain why we are doing certain things. There could be other possibilities that at first sight seem more plausible, and you as a human would like to know, why didn't you play this? So there are kind of a more depth to the explanations here. And the explanation also has to be formulated in a way that we can easily understand it. It's not sufficient, like you can just dump out all the search tree. You have to basically show the few plausible continuations and tell why they work or do not work. So I think this is a very, very rich domain for explainability, chess and similar games. I think chess might even be more suitable than other games, arguably. I know not everyone agrees with me. I've been discussing this with many people in the community because I've been trying to push for chess as a domain for this. And again, like many games, it has simple rules, complex strategies. It's a popular game, especially in this Western part of the world, and it's actually increasing in popularity. So both with COVID and Queen Gambit and things, there are many, many more people playing chess now than did a decade ago, for example. And it's always nice to have something that many people can relate to. But I think probably the main argument why I think chess is so well suited to research into explainable AI is that we have a very, very rich literature of like chess literature is very, very rich, and it's oriented towards people with different expert levels. And when we are giving explanations, there's not the level of explanation that you give depends on the audience that you have. So if you are talking to a novice in chess, you need to explain very differently than you were explaining something to a strong master. So, but we have examples of explanations at different levels in the chess. And this, and even outside games, there are not many domains that have this kind of a rich example of how an explanation should look like. And I think this is a kind of a unique, almost, in different type of problem domains, where we have such a rich set of explanations that we can actually help us in when we are formulating systems to explain the domain. And apart from that, and other games have this as well, like chess has this nice property that the complexity of the game is easily adjustable. We can work with simple end games and all the way up to very complex middle game strategies. But I just want to emphasize that this extensive literature, rich literature in that we have and can build on, this is, I think, a real asset that we have in chess that we don't have to the same level in many, many other games. Yeah, so again, if you just look at these two parts of the explanation, first is to explain like the static game states that we have, and the other thing is then the search. There are different ways for doing that. To start with, we can build transparent models like decision trees or something like that. However, they have they are easy to understand for us humans, but they cannot encode as complex information. So the focus has mainly been on like building systems in chess now that are using these complex neural networks to encode information. And then we are trying to look at what information are coded in the networks and what we can learn from it. And there are different methods for doing that. And kind of the most simplest one is just to use heat maps, highlight some squares on the chess table that are important. We can then there are other methods, and these are general methods that are kind of widely used now in trying to understand better how like neural networks. And Lime is one of those where we are using simpler models. We call them surrogate models. To like even linear models that we use to try to encode the information, like try to learn from the outputs of the neural network and try to use that to give us explanations. Shapley values is another one where we have input features and we are introducing them in different orders and looking at the marginal contribution of each features. And then kind of a more recent concept from 2017 is these concept activation vectors, where we can just dream, like we are not tied to using just the input features. We can come with all kind of features that we dream up, and we can see to this extent the neural networks is encoding these features. And based on this work, there has been quite a bit of recent works in games and chess using these kind of methods in trying to understand what these neural networks have learned. There was maybe the first really serious work was by McGrath et al. From DeepMind, acquisition of chess knowledge in AlphaZero, where they were kind of doing this independently for hacks. Michael Littman and his group were working on like similar things in hacks. And later we were kind of following up along similar lines, but so this is my PhD student and I, where we were doing, we were not only looking at the neural network, but we were also comparing that to a handcrafted evaluation function, so we could pinpoint the differences. But all these works kind of have that limitations that you have to know what you're looking for. So you have to come up with a feature and ask, is this feature in the network? Does the network know about this feature? It was not about feature discovery, but there's a very recent work out now from Oxford and Google DeepMind that they are basically trying to learn new features from scratch that the humans don't know about. And there were some preliminary studies where they were presenting these features to world-class, even ex-world champions, and basically finding out that they could present them with features that they could learn from. So even the strongest human could learn something from these networks. And oops. Yeah, and this kind of a model interpretability can take different forms depending what we are trying to achieve. It can be model agnostic versus model specific, depending if you have to know what kind of a model you're trying to explain. It can be local or global. Local means you're giving one particular game state and you're trying to understand this game state better, versus global, where you're trying to find some global truths about the game. For example, bishop pairs worth more than pairs of knights or something like that. And then if we are restricted to using only the input features into the network, or if we can just present it with other type of features that are not really used as an input in the network. This is called concepts. Yeah, so I will, in my case study, we will go into this in a little bit more detail. And again, this is just more about this things I've been talking about before. If we are restricted to using only input features, if we can ask about features that are not a part of the input, but still we have to come up with the features at the next level. And basically at the top level is we are having the system themselves discovering new features. And again, this is very, very, very state of the art now, and just recently been able to make some headway there. So this is one side of the coin. The other side in games is like the think ahead process. How do we try to explain that? And there has been some work in planning doing this. There's not been too much work in adversary domains yet. There are some kind of we have, of course, like their earlier work on chess tutoring systems that have some resemblance, but this term explainable search, where we are working in kind of adversary search domain, trying to explain the search process. There are kind of early work there, and there is some actually in-depth research being done now, and there has also like explainable reinforcement learning is kind of doing many similar things that we will be interested in when we will dive deeper into learning to explain search. So I'm not going to talk much about this, but again, it's a very interesting research direction. And let's just look at an example of how a human explanation could look like for chess. This example here is from Fisher's, Fisher's probably most known book, My 60 Memorable Games. And what is interesting here is how the explanation looks like. So Fisher is annotating his games, and in this particular position, white is checking black, and ideally black would like to, instead of evading the check by moving the king, which would lose castling right, you would like to block the check. And there are different ways for doing that. You can do that with the bishop on f8, or you can block it with your knight. Both of them would be the most plausible moves to make, but Fisher kind of makes just a comment like you could try that, but you will end up a position. It gives a very, very short line of play, only a couple of moves, and basically saying after that, like this would lead to a position where you're in an end game where your white has a knight versus a strong knight versus a weak bishop, and basically saying that that's the end of that explanation. These most plausible moves you wouldn't make, and gives a very, very short line move sequence, and then calling back to evaluation, telling you, okay, at this point you will have a ending where a knight is much better than a bishop. There's just to be able to explain something like this, like the AI system would have to know a lot. You have to evaluate, like, you know that this is an endgame that is inferior to the knight is stronger than the bishop, but you also don't want to give very concrete lines of play because that's not necessary. And so black is forced to move the king, and black can move either to the left or to the right. Fisher actually tells that it would be better, says, okay, like in the game, Rossonlini, he actually played the king to 8, which Fisher deemed to be a mistake, and said it should have moved towards the queen side because the king is safer there. Today's computer actually don't agree with that. They say that the move that was played was indeed the best in the position, but that's kind of irrelevant. The thing is the level of explanation that we are doing. So we can learn from this a lot. Now, if you have the computer evaluate the same position, it will give us kind of just the principal variation, line of play and numerical value. And you can see it starts by trying to block the check with the bishop, but then it actually falls back to moving the king. So we can learn a little bit from this, but you can see there's a huge difference in the human explanation and what we can learn from the computer. And this is, so we want to get from this to something like this. And this is actually a surprisingly challenging problem to do. There have been some systems that are trying to do this, and I think Decode Chess is a proprietary site that is saying that it's the state of the art in providing chess explanations. And you can see the explanation. It says here, it was good for black to move the king to f8 because it's threatening to move the king to a5 and check the white king. This is totally irrelevant to everything that is going on in this position, but this is more or less the state of the art today, I would say. So there's a lot of work to be done here. Many challenges. And even if you think about a somewhat simplified task of just annotating a chess game. Of course, ideally, explanations, we would like them to be interactive. But even if we just move away from that and just think about the problem annotating a chess game, like Fisher was doing here, there's still a lot of challenges we are faced with. Again, based on the audience, we might have a different types of explanation, different level of details, different type of explanations. We have to decide which position should we stop at and explain. We are not going to do that in every positions. And then we have to figure out like how much do we have to explain of what we didn't do? Like why didn't you do? What moves are plausible? What moves should you show that didn't work? And then why the line choice is the best line of play. So we are combining this, would you say, this kind of what we saw here, that you have to give some lines of play to understand what is going on, but eventually its line of play has to kind of terminate with some kind of assessment of how good the line of play is. So even though we are just annotating a chess game, there are a lot of challenges that AI systems for explainable AI would have to face. So again, and this, I think chess is the ideal domain for research into explainable AI, I think. Yeah, and I want to end with a kind of a case study where we, like a PhD student of mine and we were trying to see if we could use some of these explainability methods we were talking about to try to learn something about the neural network that Stockfish learned. So Stockfish, one of the strongest test playing engine, we used version 14.1. That was the most recent at the time when we did this research. I think that we have version 17.1 now. We were using kind of a similar methodology as the original DeepMind paper we're using, but we additionally were comparing the results from what we did to the handcrafted evaluation model, handcrafted evaluation function of Stockfish. So this version of Stockfish had both handcrafted evaluation function and the neural network, and they did disagree on many positions, and we were trying to figure out what the neural network, and the neural network was, I think, 80 or 90 ELO points stronger, that version, and we want to try to kind of figure out what did the neural network know that the handcrafted evaluation function didn't know. And so this was actually this version of Stockfish was very nice in that it allows us to do such comparison. So here, just to start with, looking at the value of the pieces, as we used these surrogate models to try to figure out some of the input features, how important they were, and more or less there was a agreement with the value of the pieces where we would have a relative to a pawn. If pawn would have value 1, there were mostly kind of good agreement between the two models and the literature values. So nothing surprising there. Then we were also looking at the how well, if we use the evaluation given by the handcrafted evaluation function. Now, if we looked at the if we looked at the score given by the neural network, how well did the handcrafted evaluation function kind of explain that, and vice versa. So so we used these here features here: material, winnable, past pan, imbalance, mobility, king, safety, threats. These are all features taken from the handcrafted evaluation function of Stockfish. And these features were the one that make up they are then combined to make up the value of the handcrafted evaluation function. And we use these inputs here to try to explain the output, the value outputted by the neural network. And it had very, very low fidelity, basically meaning the R-squared value was less than half, meaning that using these features, the handcrafted features, they could very poorly explain the evaluation of the neural network. And so that was kind of the first insight here, that there's a huge difference between the evaluation of the neural network and the handcrafted evaluation function. We looked at kind of using Schaeffer value sampling, where we are introduced these features in different order, because these features can be related. So it does matter in which order we introduce them. So like Schaeffer values, we introduce them one at a time, and we take kind of average of the marginal contribution that adding a feature does in improving the fidelity. And again, like they both agree that material is the most important evaluation features, but we saw a huge, and maybe the most important thing here is there's a huge difference in how important the king safety is. And the neural network was not very, like adding the king safety features from the handcrafted evaluation functions did improve the prediction power very little, whereas compared to in the classical model. So what this tells us that king safety, as evaluated by the handcrafted features, was not very important for the neural network. It didn't find it very useful. And so that was very interesting. And then we also basically looked into a little bit, not just explaining the decision, but where in the neural network was it encoding different concepts. And we probed the networks, different places in the network, soon after the input and later into the network. And there were some concepts, like especially this winnable concept, which is looking into, like, it's a special feature in Stockfish that is telling you how likely are you to win a position. So opposite bishop endings, would you be unlikely to win? Rook up a pawn, would you be less likely to win? And things like that. to try it so it avoids going into position that might be difficult to win. And these kind of a concept were forming, you could see the difference between the blue and the orange line were forming much, much later in the network. And then we were also looking into like positions where there was a huge difference in the evaluation of the neural network and the handcrafted evaluation functions. And somewhat surprisingly, like statically evaluating positions like these, the neural network, for example here, it evaluates, so even though black is a material in this position, it evaluates that white is much better. And it statically sees, without any search, that white can fork off by playing knight f6, it can basically fork off one of the rooks of black here. And same here, there's a race for queening a pawn. Black is to move here, and basically they both are 2 squares away. Black moving here, white moving here, but it sees that black can queen with a check. So white will not be able to queen the pawn. So here, just by statically evaluating these positions, it knows these kind of relations between the pieces, such that it evaluates them in favor of white in this case and black in this case. And like the Mathcraft paper, like by DeepMind, had seen something similar for AlphaZero, and they hypothesized that this had to do with because it was also learning the policy, like the policy network. But Stockfish is not doing that. So this ability to do this has nothing to do with one having to learn a policy to be able to see this. So this was very interesting. Also, we looked specifically at the king safety because that is what, like I said, Stockfish didn't find the way that, like the neural network didn't find the way that the handcrafted king safety feature was constructed to be very useful. And these are 2 examples where the handcrafted evaluation is strongly favoring the attacking side, like black in this case, white in this latter case, basically giving it huge advantage, whereas the neural network is very unimpressed with the attacks and basically says there's nothing to worry about, white is still slightly better in this position and black in this position here. And the handcrafted evaluation feature is looking at, like, there are a lot of open lines close to the king. The king is kind of exposed. You still have a lot of heavy pieces on the board. And basically, the handcrafted feature is looking at things like that and saying, okay, in this case, white should be very scared, and here black should be very scared. However, the neural network is not very impressed with the attack in either case, and basically evaluates the depending side to be slightly better in both cases. And so I think the way forward, for example, like how we could use this information is basically like if you want to improve on the handcrafted evaluation functions, the king safety would be the one thing to start looking at. Later, like this kind of I think it was last year, a year after we came out with results, I came across this, like there's an interview with Magnus Carlsen, best chess player, and he had this to say.
My view on the importance of king safety, short term and long term, has changed, and I think my understanding has improved so much since 2019. You have more now of an understanding of how both like taking time to build a safe king, sacrificing material to weaken your opponent's king, or safeguarding your own king. These are things that humans are intuitively not very good at. And it's a thing that engines used to be even worse at. And now these neural nets, they understand it. Well, they don't understand, but they do it so well that we're learning a lot from that. And I've had to reevaluate a lot of things for sure. My view on
Okay, so just to summarize, I think there's still a big role that chess can play in AI research when it comes to trying to have these game playing system explain what they have learned and become effective tutors, especially. And like I said before, I think chess in particular has an important role there because of the rich literature it has. It's very unique, like not just for games, but just in general that you have so good examples of how explanation would look like. So I think there's many interesting research challenges ahead in explainable AI, and I think that chess is going to continue to play an important role there. So thank you very much.
Thank you, Yngvi. Let's open the floor for questions.
So
I have a question.
Go
Yeah.
ahead, yeah.
Yeah.
Yes. You spoke about, I would say, the Carlson's quote, so to speak, about the unexpected moves. Yes, that is an interesting thing. Yes. But you know already that in the game of the world of Go, the same happens. The same happens when Lee Sedol played his match. And then in the second game, move 37 was a surprising and unconventional move. And it was made by AlphaGo, and it was in a historic match, namely against the world champion Lee Sedol. Yes, and now they have incorporated that unexpected move as a term in itself, and it is now used to describe a creative or unexpected action with any AI that surpasses human intuition and understanding. Yes. And that is fantastic. So my question now to you is, and they call it move 37. So if they said now among the Go players among each other, this was a move 37, then they explicitly point to that position. And now my question to you is, you did some research in the unexpected moves, yes? And you found some unexpected moves. Did you also find such a surprise as happened in the world of Go?
I think if we're trying to seek analogy in chess to this kind of what you're describing in Go, we didn't do that, but like the game changer, was it Matthew Chandler that had this book? We were trying to understand first when AlphaZero started to play certain style of play that is called AlphaZero style move. So it's now when you're advancing your H pawn early on in the move.
Yes.
This has been now typically referred to as playing like AlphaZero style move. So I think this is probably the closest analogy we have in chess.
That's exactly what I mean indeed. Yes, that is so that implies in effect, and that we never had I would say thought that it was so discriminating that there are two different styles. And not only a positional style and a tall style, I would say, but even in this case, with I would say surprising outcomes, so to speak.
Yeah, exactly. And as you could hear from Magnus Carlsen, like the humans are like the top humans have still the ability to learn from the play of these top engines. They understand what's going on. It's still for us, the mere mortals, we need much better guidance in trying to understand what's going on. And we could also see this in Jon Edwards' talk. Like the top experts that spend 14 hours a day looking at this, they can learn from the engines. But the rest of us needs better explanations to be able to do that.
And now
I think it's important to realize that these experts learn from these engines, but it's a long and painful process. It's not like it's very quick to gain those insights. These humans have to look at many, many examples and start generalizing, and having tried
and playing against them again and again. Yeah,
it's a huge undertaking.
Yes.
I give the floor to other questions.
So Yngvi, is there if we just follow what's happening with LLMs, is there I'll call it a training database of annotated games in chess that you could do something really simplistic like an LLM approach and gather statistics and produce as a first
Yes, very good
explanations that are
question.
just statistically based?
Yeah, so I didn't mention that, but I should have. There is now, like in the last couple of years, there have been a few works where LLMs are being used to provide both explanations, but also real life commentary. I think one paper tomorrow, I think we will even have where we are kind of seeing where chess can be used to do commentary. There has been work on using these LLMs. I think they're still very preliminary, all of them. They're not giving very useful explanations. However, there is on chess.com, I think, there is a data set of 17,000 annotated chess games, I think, by masters that has been used for this type of purpose. So definitely, I think there's interesting things to be learned from there. And I just came across this data set recently, and I think it's a huge value in that.
It should be better known inside the community because mining data sets sounds like great masters projects opportunities. So that's good.
Yes.
Let me ask one more question that sort of flips this discussion and reverses it. We're obviously interested in getting an explanation of the computer's reasoning, if you will, for their move decisions, so that essentially we get an explanation. And that would be tremendously valuable because, well, we now can have high quality computer generated annotations of games that would allow us to gain insights and perhaps make it easier for us to learn from the computer. But if we reverse that process, is anybody working on computers trying to create explainable human AI, trying to explain human decision making? Because there's
like in chess then, or
in chess, we're trying to understand these neural networks and why they made moves that they did. Humans have a different model of chess, and I would be very interested in having the computers analyze human chess play to give us an explanation of why humans made certain moves that they did.
And even try to find some
reverse?
Yeah, that's a very interesting thing. I haven't actually thought of that, but it's very interesting. And because we are followable, right? So they can even help us pinpoint some policies in our logic, how we think, right?
Well, of course, we have no fallacies in how we think, but the computer will find ways for us to perhaps improve our play.
Yeah. That's no, but that's very interesting. I'm not aware of anything like that, but it's definitely would be very interesting. There is actually an interesting chess book by was a Scottish grandmaster about what's it called, the Seven Sins of Chess or something, where it was basically looking into where we go wrong in our thought process when we are playing chess, and if computers could, for example, help us pinpoint weaknesses like that, would be very interesting.
Yes, it would be very interesting.
Oh, good question.
Okay, we have still time for a few more questions from the audience.
In my opinion, the question which we just discussed could be, I would say, rephrased on a scientific level, and that is, can we match the cognitive functions that humans have in the game of chess? That implies that creativity or intuition, that kind of feelings, which are very difficult to formulate, yeah, that he, by the help of chess situations, like we had the king in danger, for instance, yeah, could help us and could make decisions about that.
Yeah, there are definitely like I like how you flip it around. Like instead of me trying to understand the thought process of explaining the thought process of the computers, it's the other way around. Yeah. Yeah.
Yeah, I have no answer for that. That it is not a serious
no,
question
absolutely.
to be answered now, but it is more an advice for you if you still have new PhD, fresh PhD students, to challenge them with this kind of questions.
Yeah.
Let me say the general idea is, if we now try to measure the difference in playing strength, what is it? Can we give a world champion a piece ahead, or should it be a rook ahead to have an equal game?
Yeah, that's interesting. I have no idea. Yeah.
Neither do I.
Yeah.
Let me be clear. But let's say a pawn ahead is clear, although it's also still difficult. That is, even a world champion has done difficulties. But a piece ahead, it looks like that is I would say easy game for the world champion. But still, they are now also doubting whether that's still the case.
Well,
Yeah, but it's still interesting to see how chess is actually getting more popular, even though these computers have been getting this strong. So that is also, I think, something valuable to us, that like even though we have this super strong, of course, like we have this case of cheating in chess, cheating in online chess, of course, that this is a problem that is posed by, but chess is still very popular, and it's because we are humans, like we do things differently, so also what makes chess still being this much fun, right? It's kind of about
okay. Let's move on. We do have a question from Lucas. Scott has raised hand.
Yeah. Hi.
Hi.
Um, I'm curious because the explanations for the lower level players, I guess, or for the beginner level players, usually structure around the rules of the game, right? And I'm just because I'm also interested in general game playing, where this can be maybe tied in this work or in this idea. Just it's not really a question, just intuition, because maybe the rules provide interesting structure for explaining why something is more desirable than another. Not only the moves, but also the rules for why after the moves. But maybe you don't have a concrete answer to that. It's just a
no,
thought
not really.
process.
But I was working in general game playing for the longest time, and this is basically when we were trying to learn strategies for these general game playing systems. The only place, like we had, there are two places we had to look at. Like one is like by playing and learning from experience, but typically we didn't have much time to learn. In this competition, the setup was typically that you got a very little head start to learn, and then you just started to play. But this meant that the best source of learning something about the games and the strategies for playing the games was looking at the rules of the games, because this is the only thing that we were provided with. So definitely there were things that we could learn from that. If that is kind of answer your question.
Thank you.
Okay, we've gone a few minutes over, so the next session is at 20 minutes to the hour, so 16 minutes for now. So I hope you'll all join us in 16 minutes. However, let's thank Yngvi Björnsson for a wonderful talk, and I'm delighted that he's got many, many more years of research challenges ahead of him. Thank you, Yngvi.
Thanks, everyone.
Well done.
All right, so we're going to go quiet for the next 15 minutes. Thank you very much, everyone.
Thank you, Jonathan. Thank you, Yngvi.